This introduction to IO-Link is targeted to controls engineers who are going to design a new machine using IO-Link sensors and masters, or to those adding IO-Link sensors to an existing machine. This talk was originally given to the Toledo section of the ISA, the International Society of Automation. You see this marketing blitz, use IO-Link, it's universal, smart, and easy, but it's actually true. It's an open standard. It's giving communications down to sensors, and it's pretty easy to configure. One of the reasons IO-Link is successful, I think, is they got the key stakeholders together in the beginning to define the specification. When you start using IO-Link, you don't have to convert every sensor to it. You can mix and match old and new. You can send settings from the PLC down to IO-Link sensors, and they use the existing M12, M8 connectors that twist on, so that saves on wiring time, and you get more diagnostics. Just to touch on a few terms, opc-ua stands for Unified Architecture. That's just the latest version. And the industrial Internet of Things. The Internet of Things is connecting a refrigerator to the internet, and the industrial version is connecting your sensors or other plant floor devices. You can pause and read these if you want. A couple here I want to talk about. XML is just a standard configuration file. And SDCI, Single Drop Communication Interface, is IO-Link. The IEC is a standards body in Europe. IO-Link is a IEC standard. Many of us will have heard of IEC 61131-3 for PLC programming languages because PLC manufacturers have been bragging for years that they conform to this. Section 9 of this same standard is for Single Drop Communications Interface, which is marketed as IO-Link. At the end of 2017, there were over 5 million IO-Link nodes on the planet. Now, in 2019, it's over 11 million. It's arrived. Just like Ethernet IP has the ODVA, IO-Link has the IO-Link Consortium. It's an organization to promote and standardize the improvement of IO-Link. The big PLC companies and most of the sensor companies, lots of industrial automation companies are members. You can go to io-link.com to find out more. Jumping to the end, here's an overview of an IO-Link system. The PLC is talking Ethernet IP, shown in green, to an IO-Link master. The IO-Link master, in turn, is talking IO-Link to the sensor, and both of those protocols are Ethernet-based. This shows 4 separate Ethernet networks, IO-Link networks, from the master to each of these 4 sensors. IO-Link is below your field bus. It's not a field bus. These are the components of an IO-Link system. You only need the laptop for configuration. This shows the fear of many people about IO-Link, and it's not true that you're going to have to pick the right master in order to use your desired sensors, and you can really use any master with any sensor. The reality is that you can use any PLC and any sensor with any master as long as they're all IO-Link compatible. There's no compatibility matrix or charts or lookups. Some of you might have spotted the asterisk in the last slide and said, aha, but for the PLC, the asterisk just means it's got to have a field bus. You can continue to use your existing 24-volt DC sensors along with IO-Link sensors. And you can use any sensor because of the IODD, the configuration file that comes with each sensor. And we're using the standard existing connectors because they work fine. The asterisks are your cables limited to 20 meters from the master to the sensor, but it can be unshielded, and discrete PNP is called out for. If you need NPN sensors, I did not see that in the standard, although you can get IO-Link masters that do have NPN. And 4 to 20 milliamp, 1 to 10 volts is not in the specification. Hopefully by the end of this talk, you won't want to use 4 to 20 milliamp anyway. This is a cable you probably recognized, a double-ended M12 cable shielded for analog sensors. And this is an IO-Link cable. It's the same cable, but you could use unshielded. The traditional 24-volt sensor has this pinout, which is the same for IO-Link, but IO-Link sensors talk Ethernet instead of just a discrete 24-volt on or off. Next, we're going to segue a little bit into machine wiring. This is a traditional machine wiring where you wire from a PLC input module down to a terminal, and then in the field you wire your sensors through a cord grip and you land each wire individually on terminals. And this is what it looks like, which is why the Panduits, the wireways, have covers. This shows the traditional wiring where you would have in a panel shop the PLC wired like we showed down to a terminal strip, and then separately you'd have your junction box with terminals. And this thick blue multi-conductor cable has individual wires at each end that needs to get terminated and then checked and verified on site. That cable gets terminated in the PLC and in the junction box. To save money, people started using these wiring blocks, but you still have to terminate every wire in the PLC panel. They did have M12 connectors on the sensors, which was nice. Next step in the revolution was these remote I/O blocks that talk a field bus back to the PLC, eliminating a lot of wiring and a lot of wiring label. You have 24 volts that gets cascaded among the remote I/O blocks, and your sensor cables are just the standard 24 volt DC. And this does look a lot like the IO-Link diagram we started with. This is just a visual to show no analog input modules required with IO-Link masters and IO-Link sensors. Here we have the IO-Link master, which looks a lot like the remote I/O block we saw before because it is. And that had digital data, a field bus going out to that remote block. And what the IO-Link master adds is digital data all the way down to the sensor. Distributors that are successful in selling IO-Link systems do so by the cost savings of the IO-Link master, which is really the same as the cost savings of a remote I/O block, but not everyone got on board with the remote I/O blocks. It seems the additional benefits of IO-Link really help open the consideration, and the cost savings closes the deal. The extra cost to add IO-Link to a remote I/O block, according to list pricing, is about $50. And for a sensor, it seems the cost extra may be 50 cents, but the actual street price, it costs no extra for IO-Link. If we compare the wiring and the labor to terminate a traditional analog sensor to the IO-Link master, there is a great cost savings. You have no analog input cards. That's a big savings. Secondly, you have less wire, less copper. There's no junction boxes and no cord grips to deal with. Again, decision makers go to IO-Link for the cost savings, and organizations stay for the other benefits, the diagnostics and the reduced downtime. Just like people move out west for the skiing, but they stay for the summers. To summarize what we've talked about so far, IO-Link is Ethernet-based, point-to-point, from the master to each sensor, and the communication goes both ways. So you can send set points down to the sensor, and you get process data and diagnostic information back from the sensor. And we haven't talked about this, the sensor configuration gets stored in the master. So if you run a forklift through your sensor and you replace it with the identical model, the master will see it's new and will load the configuration back into that sensor, really minimizing your downtime. Most factories have devices on the plant floor networked together, and then below and between PLCs, you have your field buses like Ethernet IP and Profinet and EtherCAT. And then below that, all the way down to the sensor, that's where IO-Link resides. So you've got Ethernet in all three of these levels. Next, we'll get into some more details about IO-Link masters and then get more in depth on sensors. There's a wide variety of IO-Link masters. You can get them with M12, M8, or even M5 connectors. Some can handle outputs, some can't. A few can handle NPN. Here's a typical IO-Link master. On top, you've got your field bus coming in and out, cascading onto your next master. The 24-volt power also comes in and out. Typically, you've got two power sources, one for the sensors and the master, and a second, a higher current for outputs. This particular master has 4 connections for traditional 24-volt sensors and 4 for IO-Link sensors. This shows the power cascaded through 3 masters with the field bus also cascaded and the connected photo eyes and the traditional proximity switches. Most PLCs are artificially limited in the number of Ethernet IP drops they can have or the number of field bus nodes they can have. So if you're upgrading an existing system, make sure you check your processor because if it's an entry-level model, you may have to upgrade. Some companies offer sub-masters below the IO-Link master. A few of these are traditional sensors only on the submasters, like if you have a bunch of proc switches. Some can have IO-Link plugged into the submaster, and this will minimize your number of nodes on your field bus. Here in North America, the cheapest way to add one IO-Link sensor to the most popular PLC, which would be Allen Bradley, is using their Point IO. There's an IO-Link master that you can add if you just need a few sensors. For example, a distance sensor where you need good resolution, or perhaps a color sensor where you've got red, green, blue, and intensity. Some IO-Link masters come like this. They're DIN rail mountable to go in a junction box in case you need IP69K or if you're doing a retrofit. You could put this in an existing junction box and wire it up to the existing wiring and upgrade the 1 or 2 IO-Link sensors that you truly need. Another scenario is if you have IO-Link and you need to add a new sensor and you have in your tool crib a traditional analog sensor. They have these devices like this that go in line with your M12 cables to take 4 to 20 milliamp or 0 to 10 volts to IO-Link. So you don't get the benefit of the higher resolution of IO-Link, but this is a good product for the transition. We're going to take another brief sidebar into sensor evolution. From the 90s and earlier, we have the traditional single output proximity switch. Even a simple proc switch, you could get lots of other information from it if the voltage is low, if it's over temperature, perhaps vibration, what's the magnetic field strength, or maybe you could linearize what's the distance to the object. Today, even the smallest photo eye has 5 wires. It'll have an extra output or an extra teach input. Larger ones will have 8-pin for, again, multiple outputs, analog or discrete, or multiple inputs to select different profiles. Some sensors will have serial RS-232, RS-485 for bidirectional communication, and also for higher resolution. Most analog sensors, 4 to 20 or 0 to 10, have 12-bit A to D converters, and most PLC input cards are also 12-bit. So you're limited in the resolution that you can get into the PLC. So our photo eyes have gotten better than this 12-bit limitation. Some of you may be thinking, yeah, I don't need this fancy new protocol. I've been programming serial for years. And you can do that, but here is a flowchart of a robust program with retries and timeouts. Contrast that with IO-Link, where once you configure it, the data in your IO-Link master and up to your PLC just get updated as if by magic, because that's what it is. Each IO-Link sensor comes with an IODD file, an input-output device description, which is like an EDS or a GSD for Ethernet IP and Profinet. It's in an XML format. the IO-Link master has to have a copy of the IODD for each unique sensor connected to it. And that IODD file is in a zip format that contains the text file, the XML file, and a bitmap or two of the sensor itself. When you're commissioning a machine or doing a startup, it's really nice to have that picture of what the sensor looks like when you have multiple sensors, just to make sure you have everything correct. When you load the IODD, load it as a zip file. You don't load the two components separately. XML is a decades old, open and proven standard. You can understand it, you can read it. So the point of this slide is that people can read it and understand it, and machines can also understand it. And this kind of also goes towards how can any sensor and master work together from different vendors. You don't need to know XML because your sensor vendor will provide an IODD, a data map of how all the bits and words line up in your master and in your PLC. There's different kinds of data codified in the standard. There's cyclical data for process, for example, your distance from a photo eye. There's acyclic data, such as your set points or updated configuration. You have different commands that can go down to the sensor and different events that can spontaneously come back. Again, the terms are process data, service data, and events. Process data is fast. For example, distance. Service data are things like the vendor ID and the model ID. Events can be sent from the sensor when they happen, like a weak signal. COM is for communications operating mode. That's really the speed. Service data on startup, the ID is used to load parameters if it's a new sensor of the same make and model. The IODD file typically does not ship with the sensor. There's no CD, there's no memory stick. You can get it two ways though. One way is from the sensor manufacturer's website directly. Another way is from the IODD Finder at ioddfinder.io-link.com. And it's up to each manufacturer to voluntarily put their IODD files up there. There's a couple of ways to load the IODD file depending on which master you have and which PLC. You can sometimes use software provided by the master manufacturer, and some PLC programming packages could also load the IODD file when you configure the whole network. The best way, in my opinion, having used them all, is when you have a IO-Link master that has a web server built in, and you just do it from the browser. It's quick and easy, no software to install. You don't have to worry about having the right version of the software. Everybody can do it. Even the maintenance guy that works graveyard, unless you like taking those calls at 3 a.m. on a Saturday. Thanks to David Letterman, it seems like we need a top 10 list. Here's mine. Top 10 reasons to use IO-Link. I'm not going to read them to you, but if you want to pause and look at them, you can. And you can pause on the second half. The next logical step in this evolution that I want to talk about has actually already happened. There's companies that have had products like this out for a couple of years. We still live in a PLC-centric world. Everything comes into the PLC. If you have an operator interface, the database, the tag names are typically in the PLC. All of your I/O comes into the PLC. Sometimes you massage the data, and then higher level services, historians, SPC, EMS, all get data directly out of the PLC. PLC I/O has microsecond or faster update times. Some data has an update time in seconds. So the PLC is great at handling that faster I/O. Here is the future that already arrived. We've got our PLC in its traditional role where it thrives with discrete I/O, fast processing, and separately from that, we can go directly to a database or a historian or an EMS or a cloud, down to our distributed control, down to our IO-Link master. So the PLC I/O update times are preserved and retain their high priority as it should, and then a lower priority is the cloud communications to our database. Here's the same thing shown a different way, where you have your PLC in the upper left talking to drives or other high-speed I/O that's shown in green. And then down below, you've got it also talking to your I/O link masters. And separately in purple, you've got this lower priority channel, opc-ua or MQTT, for example, to go to things like a SQL database, an HMI, the cloud, or a local server. We have these terms that just drive me crazy, like the industrial Internet of Things. To me, if you have opc-ua and IO link, you've got the industrial Internet of Things. And big data, what's that mean? Well, you save lots of data to a database, and then you analyze it using things like SPC to do predictive maintenance. There is a draft document open for comments for adding opc-ua into the IO link standards, but there are some IO link masters you can buy with opc-ua today. As of right now, they're working on a specification for IO link safety. Here is a list of some things to consider when you're out looking for an IO link master. And first of all, obviously it has to have your field bus, but the other things I'd look for is the diagnostics. In particular, what are available without any additional PLC programming. Typically this means having one with a web server so you can quickly get at that diagnostic information to reduce your machine downtime without any additional PLC programming. Of course, it'll be even better when you can, or if you're doing it from the ground up, to have an alarm on your HMI. But once the machine is down, this is a quick way to get at a sensor problem with no additional work. Next, look for one with submasters to minimize the number of nodes on your field bus. Obviously, consider your IP rating and think about what kind of data archiving protocols do you want. Find an end product like Ignition or Azure that you want to use, and then find an IO link master that has that. And I just encourage everyone to try one. Do a pilot study, do a pilot machine, and then from there you can make some more informed decisions, and all the IO link manufacturers are going to be improving their products. So even if you chose poorly, you still have some good data about the true cost savings and the benefits of IO link. Here's some references. If you want to connect with me on LinkedIn, I'm the engineer in North America, not the music conductor in Australia.